All right. Hello, everybody, and welcome to my home, which is the place where I will continue teaching ATMO 412 for the foreseeable future. I hope you're doing well. I hope you had a fantastic spring break, you recharge your batteries, and you're now ready to go through the remaining topics to finish this class, which I hope you're enjoying. Before we start talking about France, which is today's topic, I would like to take a moment and remind each and every one of you that the threat that we're facing because of the coronavirus is a very serious one. And so I'd like to urge you and encourage you once again to take this very seriously. Please do not panic, but at the same time, be concerned and take good care of yourself. I am sure that facing this on your own, far away from home, some of you are coming from the mainland, some of you are coming from other countries, some of us are coming from other countries. I'm sure that having to face this on your own is not easy. And so I would also like to remind everyone that you are not alone. We, as faculty in ATMO, we are here to help you as much as we can. You have my email address, you have my cell phone number, you have my Skype contact. You have many ways to reach out to me. Please do so if you need anything. If you're scared and you want to talk to someone, if you have some health concerns, if you're not sure about something, if you need some food because you ran out and you don't want to go to the stores, I can assure you I have more pasta in my kitchen cabinets than I could possibly eat in the next 2 months. So if you need pasta, please feel free to reach out to me. I'll be more than happy to bring it to you. Actually, I'll be more than happy to cook it and bring it to you because I don't trust your cooking. No, I'm just kidding. But anyway, please take the coronavirus really, really seriously. This having said, I think we can start. This is a new format for you, and it's a new format for me, so I hope that we can make it work. Again, through the contacts that you have, please let me know if there's something that is not working. Let me know if you have problems, if you have troubles accessing some of the material, if some things are not clear. I sent the guidelines over email as to how we should continue the class. If some of these guidelines are not clear, please reach out and let me know and we can discuss. Okay, without further ado, we can start talking about France today. First of all, before we start, we should always ask the question of what is the front? What is the object that we're going to talk about today? Well, this is a bit of a tricky question because, as is often the case when talking about complex sciences and complex topics, it is really hard to give a precise definition of a front. We all have some general idea of what a front might be, but providing a clear, non-contradictory, consistent definition may actually be a little challenging. So generally speaking, we should think of fronts as areas, relatively narrow areas, small areas, of enhanced temperature gradients. Now, this is what we should keep in mind as sort of as a way to conceptualize or idealize fronts, but you can immediately understand why this definition could be problematic. Now, imagine the following case where think of the mainland, okay? The eastern part, southeast and the east coast, they're covered by relatively moist air, and the western part, Great Plains and Midwest, whatever, they're covered by really dry air. So at night, because of radiative cooling, the dry areas cool down more than the moist areas. And so if you were to look at surface temperatures at night, you would see potentially a sharp front that separates these two areas quite clearly. However, during the day, when the sun comes out and it starts shining on the land and the heat from the land is transferred to the air, it takes less to heat up dry air than it does to heat up moist air. And so the western part, which at night was really, really cool, now it becomes really, really warm. The diurnal cycle of temperature is typically greater over drier atmospheres than it is in moist atmospheres. And so the front that was so sharp and so clearly defined at night is not as sharp during the day. And so if you were to use only temperature as a way to distinguish, to find the front, then you may be in trouble already. So a better way, a less rigorous, more vague, let's say, but a better way maybe to conceptualize what a front is we should think of a front as a boundary between two different air masses. And the different air masses could be many. It could be, for example, it could be marine, warm, moist air, and continental dry air. Okay, when these two meet, there will be usually sort of a line, almost of discontinuity between the two. Okay, and this line is the front. Even though properties such as temperature may change during the day, these two remain kind of separate in a way. A better way maybe to define the fronts, instead of using temperature, we could also use other quantities that may be more useful. One could use density temperature, or even better, density potential temperature. Density potential temperature, I remind everybody, is a form of temperature that takes into account the density of the air. It could be considered as a proxy for density of the air masses. Or we could use the equivalent potential temperature that takes into account the moisture content of the air. So if we were thinking about the dry air and moist air example, certainly the dry part would have a diurnal cycle that would make it oscillate more than the moist air. But because equivalent potential temperature is taking the water-vapor mixing ratio into account, that may help kind of offset this weird effect that would smooth out the front. Another important question that we have to ask ourselves is, why are fronts important? Why are we thinking about fronts? We introduced the notion of fronts in the last class when we talked about extratropical cyclones, and we talked about the Bergen model of extratropical cyclones that was developed at the beginning of the 20th century. Now, we said that model, had been sort of modified through the years, but the notion of fronts, even though it isn't as crucial to the development of extratropical cyclones as Scandinavian meteorologists originally thought, the notion of front is still an important one. Fronts are associated and contribute actively often to the formation of, to the generation of severe weather events. I'm thinking about supercell storms, for example. Often fronts are associated with really strong wind shear. And wind shear, together with enough heat and enough moisture, is capable of generating supercell storms, which often lead to significant amounts of hail or tornadoes, which can devastate different parts of the country. Also, fronts do not have an impact only on the surface, but can also impact sort of the higher altitudes in the atmosphere. There can be elevated fronts, for example, and these would have an impact, for example, for aviation meteorology, sort of generating, for example, clear air turbulence, which, it may not destroy an airplane, but it could cause damages to airplanes and things like that. Now, let's start to dig into fronts a little bit more. France, we said, the defining characteristic of France is that there typically is a strong temperature gradient, horizontal temperature gradient. Temperature gradients we saw at the beginning of this course, we saw that temperature gradients are associated with wind shears. And if you remember when we talked about the geostrophic wind, thermal wind balance, and QG equations, you remember we said that essentially the geostrophic advection caused the weakening of the thermal wind balance. And in order to restore the thermal wind balance, an ageostrophic circulation was generated. Okay. Now, we may think that something similar would happen here. We have likely some circulation along the front. We have temperature gradients. And so it's not unreasonable to think that we may actually have some ageostrophic circulation going on here. And this ageostrophic circulation may interact with the weather, may cause some of the weather. And so this is really something that we should start to try and understand. Before we do so, however, let's think about this for a moment. You may ask, since we developed this beautiful QG framework to look at synoptic weather in the mid-latitudes, why can't we just use QG here and be done with it? Well, we'll see a few examples now, and we'll see a few examples of what the weather or what fronts look on weather maps. And you'll notice that fronts have essentially two length scales, if you will, that can be associated to them. One length scale is sort of an along the front scale, and this can be as big as synoptic scale. It can be of the order of 1,000 kilometers or even more. But there's another scale, which is the cross-front scale, and this tends to be a subsynoptic scale of the order of 100 kilometers or even less at times. And so, while QG approximations may be used to, make considerations for along front direction, things across front, which is really where the temperature gradient happens, these are not good enough for QG approximations. Remember that QG was based on the assumption that the Rossby radius, velocity scale over Coriolis parameter over length scale, this was small, was of the order of 0.1. But now the length scale, all parameters unchanged, so U and F unchanged, the length scale now across front is a lot smaller. And so the Rossby radius might actually be of order 1. And so QG cannot be used in this case. Sometimes people talk about SG, semi-geostrophic approximation, but I don't want to complicate things too much. So this being said, fronts obviously come in different shapes and different forms and different varieties, but there are some characteristics that fronts tend to share. First of all, we said temperature contrasts. There tends to be a minimum of pressure and a maximum of cyclonic vorticity along the front. Typically, also we have strong vertical wind shear, and also very often horizontal wind shift. So the wind direction actually changes across the front. We tend to have large static stability within the frontal zone. We also often observe ascending air and therefore clouds and precipitation near the front. More of this later. And also, the front tends to be, at least for surface fronts tend to be more intense at the surface and lose intensity as we go higher up in the atmosphere. Again, more of this later. As we said before, fronts can also be sort of aloft, upper level fronts, and these have impacts for clear air turbulence and aviation meteorology. Okay, very good. Let's look at some examples to have some ideas of what is going on here. This first example is a NAM analysis field. Well, NAM analysis, few fields from a NAM analysis that refers to a situation from 17 November 2009 at 00 UTC. The panel on the top left is representing, in the blue lines, has sea level pressure, and the red and the blue line are sort of subjective position or subjectively identified position of the cold and the weather front associated with this particular system. Panel in the top middle, let me double check. The red lines are equivalent potential temperatures, equivalent potential temperature contours, apologize. And the blue line is still sea level pressure. Now, the panel on the top right still has sea level pressure, but the shading now refers to cyclonic vorticity. And finally, bottom left is a cross-section. The cross-section refers to the dashed line in the top left panel. And here you can see wind barbs, and you can also see potential temperature contours in red. Okay, so what are the first things that we're observing here? First thing is, as we said, the presence of a low pressure, minimum in pressure, in the northern part of the cold front. Notice if you look at the equivalent potential temperature contours, notice how tightly packed they are next to both the cold and the warm front, okay? This is a clear indication of front. So as we said before, a relatively narrow area where temperature changes really rapidly. We also observe, if you look at vorticity, as we said, cyclonic vorticity particularly along the cold front. So you can see there are a few maxima. There is clearly a maximum where the low is located, but there are also other maxima along the front. And this is also one of the reasons, if you remember, that we said this is also one of the reasons why the fronts are often preferred locations for the generation of extratropical cyclones. Pre-existing fronts can be conducive to the generation of extratropical cyclones, just because they can be a reservoir of cyclonic vorticity, if you will. And finally, look at how the wind is shifting. When you look at the vertical cross section, notice that east of the front, notice that the isotropes are sloping here, which again is another way of locating the front. East of the front, the winds veer, but there is actually strong backing west of the front. So as we were saying before, there's like horizontal wind shift as the front passes. Okay, let's start talking about now one thing called kinematic frontogenesis. And by this, I mean, what are the processes that can act as forcings of fronts? Kinematic frontogenesis is to distinguish from dynamic frontogenesis that we will talk about in a moment, that deals with the ageostrophic circulation that I mentioned earlier. So, in order to study the kinematical frontogenesis, we introduce a function that is often referred to as the frontogenesis function. And there are many ways to define this. We use potential temperature, and we use a definition that we owe to Pedersen. And this function is simply the Lagrangian or total derivative of the absolute value of the horizontal gradient of potential temperature. Okay. Now, a couple of things. First of all, why are we talking about potential temperature now and not temperature? Well, remember that the real world has topography. And so if you consider temperature, if you look at a weather map of the United States, temperatures over the Rockies will certainly be different than temperatures on the Great Plains, but how much of this difference is due to the fact that you're part of different air masses or there are different weather phenomena going on, and how much is it really just due to the adiabatic cooling that the air experiences going up? And so we use potential temperature, so we bring everything down to a reference pressure, 1000 millibar, typically in this case, and so we're happy with it. Notice that we're dealing with a total derivative, so we are following the front as it moves near the surface. Okay, we're not at a fixed position. We are adopting a Lagrangian viewpoint. We're moving together with the front. And also, to simplify the math a little bit, from now on, we will move the axis. We will rotate the axes in such a way that one direction is perfectly aligned with the front and the other direction is perfectly perpendicular to the front. Let's assume that the front is just a line, okay? It's a quasi 1D structure, okay? And we will assume that X is the direction along the front and Y is the direction across the front, okay? Now, if we assume this, then the potential temperature will only change in one direction, of course. Now, if you do this, if you assume this, then the frontogenesis function f, you can actually expand it out. And this can be expanded out in 4 different terms. The term in orange color that you see on the slide is called shearing term. The blue is a confluence term. Then we have a tilting term, and finally a diabetic term. Okay, now we will go through some kind of examples or conceptual idealizations just to appreciate what these mean a little bit better. Please keep these functional forms in mind. So these different terms in mind as we start. So the first term that we want to consider is that we want to think about is the shearing term. Okay. Now the shearing term essentially has to do with wind that happens to compress potentially the isotopes. Now look at the picture on the left. This is an idealized front. We have a cold front that we can see with the blue line, and we have some isotopes that are given here in Celsius degrees. And there's also a warm front to the north. The arrows indicate the direction of the wind. Okay, notice that the wind is sort of advecting, is doing cold advection to the west in the cold sector of the front, and advecting warm air in the warm sector. Okay, notice that in both cases, the wind acts to essentially squeeze the isotopes together, bring the isotopes together. Okay. So the 5-degree isotope, for example, or isotherm, if we want to think in terms of temperature, is pushed towards the cold front, and the 30 degrees, so it's pushed southward, and the 30-degree isotherm on the warm sector is pushed northward. Okay, so if you look on the right, as you can imagine, this will lead to an intensification of the front. Okay, because it exacerbates an already existing temperature contrast between the two. Now, does the shearing term always contribute to the intensification of the front? Well, of course not. If you look at what the shearing term looks like, obviously it contains the delta theta delta x, which is the temperature contrast, but it also contains a delta u, a du dy, which is it tells you how the wind is changing in the y direction. And so if the wind, instead of advecting cold air towards the front to the west and warm air northward, if it's directed in a different way as it is on this slide, then the opposite happens. Notice along the warm front on the north, noticed on the northern sector that the winds now are essentially advecting warmer air towards the cold area. Okay, so there's warm advection to the north. And so if you then look at the right side, it's as if these isotherms were lifted in a way. And this is a manifestation of the fact that now the du dy term changed sign. And so the forcing is now negative and it weakens the front. Okay, so let's keep in mind the fact that the shearing term not always acts to intensify the front. Next term that we want to consider is the confluence term that we defined before. Now, the confluence term does not have wind, is not given primarily by wind that is blowing sort of along the front, but it's more wind that is across the front direction, in the across front direction, okay? And another way of saying this is mathematically, instead of having a du dy, which is what the shearing term had, now the confluence term has a dv dy, and the v is the wind across the front. Okay. Now look at the pictures here. You have some wind to the north of this front that is pushing cold air, essentially squeezing the isotherms down, and in the south you have exactly the opposite. Okay, so both from the north and from the south you have a squeezing of these isotherms that will eventually lead to an intensification of the front. Okay, and you may think this may give you the idea that this will probably be a problematic term, because this is going to increase dramatically the thermal wind. And if you're increasing the thermal wind, something has to happen in order not to destroy thermal wind balance. So wink, wink, nod, nod. Ageostrophic circulation. We'll talk about this a bit later. Also, the confluence term is typically an order, well, not typically, I would say is often an order of magnitude greater than the shearing term. Okay, so this can be a really significant term for the front itself. Next, we had a tilting term. Now, the tilting term depends on the vertical velocity. It has a d omega dy, okay, and how the vertical velocity changes as we go across the front. Now, vertical ascent is admittedly relatively weak along the front in the lower troposphere. But there can be things that exacerbate these motions. That can be significant topography that leads to katabatic or anabatic winds or katabatic winds that contribute to the tilting term. So this may not be important at the surface in general, but there may be things like mountains and topography that will lead to an intensification of this term, and also this term could be important aloft. Okay. And finally, the next term we should think about is the diabatic term. This is the last term. It contains the d theta dt that shows up every time we have diabatic terms. And this term has to do with essentially with processes that that can be related to what is happening outside of the front in a way, in the boundary. Let me give you an example. Suppose you have, as you're seeing in the picture here, suppose you have a region that is, for example, as a kind of terrain that heats up really, really well during the day and cools down a lot at night. So the cooling down of the terrain could potentially lead to an intensification of the front, for example. Okay, so anything that may contribute to differential diabatic heating. So the fact that the diabatic heating is affecting different regions of the front differently, the cold region and the warm region affected differently. These could contribute. So things like different surface properties, different soil moisture content, the fact that maybe the cold front is covered by a very thick cloud deck, and so it doesn't heat up during the day, and so it stays cold, and the warm part is actually warm, and it gets warmer. Or different water vapor content, for example, can lead to different radiative heating in the atmosphere. Okay, all these contribute to the diabatic term. Now, even though we're not going into the details of the diabatic term too much, you should keep in mind that diabatic terms can actually be important, and they can actually be significant enough to be visible. So let's look at this example of a front. This is a NAM analysis of a front that is propagating over the mainland in November 2007. My throat is getting super dry. I hope I won't lose my voice. But anyway, this is November 2007. We have essentially 4 days. Notice the cold front that is starting, and it's pretty visible over Texas, more or less, and then it sort of propagates out. Notice 15 November how the black lines, which represent equivalent potential temperature contours, dash red lines are sea level pressure. Notice how the packed equivalent potential temperature contours over Texas tell us that there's a really marked front. But notice that as soon as the front moves over the ocean, over the Gulf of Mexico, for example, notice how more spaced out these lines become. It's interesting that and the same happens actually at November 17 as the front moves over the ocean and presumably evolves into an extratropical cyclone, judging by the shape. Notice again how the isotropes get kind of spaced out. Interesting to notice, just to highlight the importance of different surface fluxes and different surface properties. Notice how November 16, notice how you can actually see the Florida Peninsula from the equivalent potential temperature contours. Like these contours are spaced out really, really well over the ocean, but over the continent, they're still quite packed together. Okay, surfaces are different. They have different ways of heating up. And this shows up in the way that isotropes, that equivalent potential temperature contours are kind of packed together. Okay. Now we're thinking about 2D, but fronts are not we thought about 1D. All the descriptions that we gave was about one-dimensional systems. Okay, there was a sort of a cross. There was a shearing term or a cross term, etc. Things in reality are a bit more complicated, and fronts really have a 2D structure. And so in general, things are slightly more complicated when we consider, not more complicated, but there's literally an added dimension to the complexity of dealing with the problem. Okay. Very good. So enough about the kinematic frontogenesis. We can now move to dynamic frontogenesis. And the dynamic frontogenesis deals with the processes that have to do with the ageostrophic circulation that I mentioned before. So when talking about the kinematic frontogenesis, the front was almost a passive spectator. There was some kind of forcing, and this led to an intensification or weakening on the front. However, remember when we talked about the thermal wind balance and we talked about jets, we said, well, geostrophic advection leads to a disruption of thermal wind balance. Okay. Now, I know I just said that QG doesn't work here, but in the derivations that led us to conclude that thermal wind balance was going to be disrupted by the geostrophic wind, I think it's reasonable to expect that the considerations that we made could be applied here as well, even though QG framework doesn't really work across the front. Okay, and so this increasing temperature gradient and the strong temperature gradient and the strong temperature gradient associated with the fronts may actually be not the whole story. Okay, there may be some ageostrophic circulation evolving in order to balance things out, if you will. Okay, and this circulation actually turns out to be important for the evolution itself of the front. Now, as we said, QG was good to get some kind of intuition of what may happen here in terms of the processes. I just realized that these look like giant hens. I'm sorry. I'll try to keep them away. There is no giants with me, however. So these are really my hens, just a bit too close to the camera. I'm sorry. So I have to get adjusted to doing this. Okay, so QG was good to get some kind of intuition of what may happen, but not good to derive the math. Okay, so if you want to do the math, we have to follow a different approach. Okay, so let's start with the equations of motion. Let's make the usual simple approximations, and we'll assume Boussinesq approximation as well. And we will divide the atmosphere essentially in two states, a base state, kind of at rest, and any kind of deviation from this state. On the slide, you can see a few equations and a few definitions. Starting from the bottom, this is essentially deviations from the equivalent of the geostrophic of the geopotential height. Okay, these are deviations from the base state of the atmosphere. Rho 0 is a density that we assume constant as per Boussinesq approximation, and phi prime reflects fluctuations in pressure at a different location at a different height. B, moving upward, B is the buoyancy. And buoyancy is obviously related to fluctuations in temperature. And these you can show are related to the vertical gradient of phi prime that we defined underneath. Okay? And moving up onward, we have the two momentum equations. Okay? where we have, notice that we have the first term are Lagrangian derivatives, okay, du dt and dv dt. So following the motions, and so these have to be expanded out. Then we have Coriolis as usual, and we have the pressure gradient force. We are neglecting friction, remember, but this is usually a pretty good approximation. I don't think we should spend too much time on the derivations. I would encourage you to look up all the technical details on the textbook if you're interested. I would much rather get to the point, but let's nevertheless navigate through the different steps, okay? The first steps are to derive a thermodynamic equation, and this is sort of a standard procedure, and we get some evolution equation for the buoyancy, which is also an evolution equation essentially for temperature fluctuations, if you will. And this, unsurprisingly, is related to vertical velocity and the Brunt-Väisälä frequency. And then we have a continuity equation, but notice that even though we cannot use QG framework here, we can still divide, obviously, the wind in geostrophic and ageostrophic, okay? And the geostrophic wind still satisfies the usual definition, and therefore the horizontal gradient of the geostrophic wind vanishes, which means that we have two different continuity equations, if you will. One for the geostrophic wind, and one that relates the ageostrophic wind and the vertical velocity, okay? Given these, we start massaging equations a little bit. We separate geostrophic and ageostrophic wind. Where is the trick here? So, and in what ways is this different from QG? Well, if you remember, in QG, we said, well, the ageostrophic circulation doesn't matter, and so we can ignore it, we can neglect it, don't consider it in the equations anymore, okay? We drop the term. Well, here we don't, okay? That assumption is not justified anymore, and so we have to keep it, okay? So the momentum equations and the thermodynamic equations can be written as you can see on the slide. Feel free to pause if you want to stare at them for a good minute. Again, I don't want you to focus too much on the technical details of the derivations. It's important to know how things are derived, but that's not the aim of this class, okay? So please look at them, think about them, but let's not focus too much at the moment. Finally, we massage equations a little bit, and using the thermal wind balance equation, enforcing essentially the thermal wind balance, which is the third equation on this slide, can show easily that the thermal wind balance can be written in this way. Remember, thermal wind balance relates vertical gradient of horizontal wind with meridional, or in this case, so local horizontal changes better. Horizontal changes of temperatures is related to buoyancy here, okay? And so because in the previous slide we had an equation for buoyancy and an equation for the momentum, UG, we can massage things a little bit and obtain the two equations at the top, and because of the thermal wind relationship, we can equate these two, okay? We can equate the right-hand terms, cancel out what is not needed, and this will give us an equation for the ageostrophic circulation, okay? Or an equation that relates the ageostrophic circulation, VAG, and the vertical velocity. Actually, even better, remember that we introduced the geopotential height, and we said that the geopotential height was essentially, the geopotential function was essentially a string function for the geostrophic wind, okay? In an analogous way, we can introduce a string function for the ageostrophic circulation. So if we go to the next slide, we can define psi AG, and VAG and W are related to the string function with the equations with the top two equations on the slide. Well, if you use this equation, then the things simplify considerably, and we can finally end up with a pretty neat equation for the stream function, for the ageostrophic stream function, if you will. And what this is telling us is that, we have some geometric properties of the stream function. So notice that we have second derivatives in y, second in z, and we have a cross derivative. So this is kind of like a rotated Laplacian in a way, but so some kind of geometrical property of the string function equals the Q2, the second component, the y component of the Q vector that we had seen when talking about QG equations, okay? So there's something very similar in the approach here. Something very similar in the conclusions, in that we still find an ageostrophic circulation like with QG framework, and we still have the Q vector popping up, although things are a little bit different. And we got to this point because we decided not to ignore the ageostrophic circulation, the ageostrophic advection, essentially. Okay. Excellent. Now here we wrote it as Q2 because it's the y component of the Q vector. But often, because fronts may not be aligned with the coordinate systems that you have, it's customary to find this written as QN, where QN means the component that is perpendicular, sorry again with the giant hands, is the component that is perpendicular to the front, okay? Very good. So this is known as the Sawyer-Eliasson equation, and it's super important because it essentially tells us how the ageostrophic circulation associated with fronts work. Now let's try to build some kind of graphical intuition of this. Okay, and let's start with a simple cartoon that you can see here. Now on the left, you can see the sort of the initial time, and on the right, it's some time later. The dashed lines are isentropes. We start from colder to warmer going down. The red arrows are horizontal wind vectors, and the thick black arrows are the Q vectors. Okay. Now, the Q vector here is directed towards warmer temperatures, which means that Q2 is negative. If you apply the definition, you'll find, if you apply the definition of Q2, you'll notice that it's negative. In particular, because of how we set things, UG is 0. Okay, so one of the terms in Q2 vanishes. We only have dVg dy multiplies d theta prime dy. Okay, and both terms dVg dy and d theta prime dy, close to the fronts, they're both negative. So negative, negative, negative is a negative number. Okay, so Q2 is negative, and in general, whenever we have that the QN vector, so the vector that is perpendicular to the front, whenever this QN points towards warmer isentropes, then the geostrophic flow is being frontogenic. Okay, so it's squeezing the isentropes and increasing the temperature contrasts. Otherwise is frontolytic. Okay, it's lifting the front. Okay, so the resulting ageostrophic circulation is seen here. Now, AB is a cross section along the front. The cold is the B side, and the warm is to the left. And notice that this ageostrophic circulation, essentially, what is it doing? Well, it's lifting the air in the warm side, and it's making it sink in the cold side. So while the front intensifies, okay, the ageostrophic circulation acts to weaken the temperature gradient a little bit. Okay. Thermal gradient tightens, magnitude of Q2 increases. This circulation increases as well, and it kind of diminishes the temperature gradient a little bit. Okay. Now, at this point, so you may ask, why doesn't the ageostrophic circulation offsets the tightening of the thermal gradient then, right? So you have a front that is intensifying, okay? You have this confluence that is bringing the isotopes together, okay? The ageostrophic circulation acts against this, okay? So why doesn't this balance things out altogether? Well, as it turns out, if you were to do the math exactly, you would find that the circulation isn't really very strong at the surface. So the front intensifies at the surface, but the vertical velocities at the surface are not strong enough to weaken the front there. They may have an action aloft, but not near the surface, or not as much near the surface. And so the front can intensify still near the surface while weakening a bit as a result of this ageostrophic circulation. Higher up, okay? And finally, notice that often, depending on the orientation of the front, we may actually have to take into account Coriolis force, and in particular, the Coriolis torque, which could actually strengthen the along front shear. Okay, very good. Okay, so we want to look at some examples as we go on. This is a GFS analysis that you're seeing here is a GFS analysis that is valid 12 UTC 14 November 2008. Notice that we are over the ocean. You can see the contours of the West Coast and British Columbia to the left. I have to use the book because I can't see really well on my laptop. And you can see, a couple of things. On the top left, we are looking at wind barbs, so wind direction and wind intensities. The red lines are 1,000 millibar isotopes. So these are telling us that there is a cold front and there is another frontal structure, a warm front, almost on the west coast, pretty much. The top right figure, still wind barbs, sea level pressure in contour lines, and the colors, the shadings are cyclonic vorticity. Sorry, I misspoke, not cyclonic vorticity. It's the horizontal frontogenesis function. I apologize. Now, the figure C, so bottom left, it's kind of the same as top right, but we have the addition of QN. Okay. And finally, the bottom right has still QN. The red lines are sea level pressure, like top left, and the shadings are the vertical velocity. Okay. Now, a few observations. The first thing is that on the warm side of the frontal zone, it seems like we have what we call shearing frontogenesis over there. Okay. Notice also that we have frontogenesis function is positive and strong, particularly along the cold front. Notice, look at the QN vectors and notice how strong they are, unsurprisingly, obviously, how strong they are, particularly along the cold front over the ocean. Okay. Correspondingly, having such strong QN vectors, we also have negative values of omega along the cold front, so ascent ahead of the cold front, and descent behind the cold front, and the other way around along the warm front. So to the northwest of the warm front, there is positive, so it's descending motion, and behind there is negative values of omega, and so ascending motion. So the ageostrophic circulation that arises is essentially a response that should weaken at least a little bit the temperature gradient. Now, if you don't believe me that there is this vertical velocity, let's actually cut a cross section, and we cut it along the black line that you see in the bottom right. And if you look at the vertical velocity along that cross section, then that is represented by the figure here. Okay, this is essentially the ageostrophic response in a particular region. The black lines are isotropes with 5K interval in this case. Okay, so negative means essentially air rising, and positive values are in sinking motion. Okay, so now that we've seen the basic elements of basic kinematic and dynamical elements of the fronts, I would like to conclude pretty much by introducing a little bit of terminology and talking about the different types of fronts that we may come across. The first kind of front, and one that we've already talked about and that I'm sure that you've heard already, is the cold front. Okay, cold front, as the name suggests, is characterized by the advance of cold air mass in time. Okay, these can cause severe weather often. If there is enough moisture, if the wind is aligned in the right direction, there can be severe weather events following the passage of cold fronts. Now, there are actually different types of cold fronts, and the differences are due to the front relative orientation of the warm conveyor belt of the associated system. Okay, and these two basic structures are called catafront and anafront. Okay, if you want to see a graphical depiction, this is what they look like. Now, essentially, before we delve into these names a little bit more, catafront is a type of front that cold front with a catafront structure is a type of front that crosses that doesn't cross, that travels parallel to the cold front and doesn't cross it, whereas the anafront crosses the cold front. Okay, this should keep in mind. If you keep in mind these arrows, these are kind of useful to keep in mind the difference between the two. Okay. So cold fronts with catafront structure are characterized by a lack of ascent in the warm conveyor belt along the surface cold front. Okay. Now, often when we have these type of fronts, we have cold and dry air that is pushing the front aloft. So if you look at the top right figure, you can see this is an example, a sketch of what a catafront or cold front with a cataphront structure might look like. And you can see that while this is kind of along the front, if you will, a cross-section along the front, and while the front progresses, you have the warm conveyor belt to the right, and this generates some precip, but aloft in the cold sector, you have cold and dry air that is pushing forward, okay? Because there is this cold front aloft, this will typically limit the extent of the clouds that can be generated. And so often it doesn't let these clouds grow tall enough to generate mixed phase precipitation. And so usually these are associated more with lighter precipitation. So things like drizzle, for example. Okay. Nevertheless, because you have particularly dry air, you can have particularly dry air, low theta E or theta W air aloft. These situations can lead to unstable soundings. Okay, you have theta E that decreases with height, and so potentially, if you had the right amount of lift, you could still have significant amounts of precipitation. An example of these systems is given by this image in the on the bottom. This is an example of a cataphront from 18 UTC 31 December 2002. And you can see sort of radar images of the system with the surface analysis as well. Okay. Second type of cold fronts is cold fronts with an anaphron structure, or we can call them anaphrons. And in this case, the warm conveyor belt crosses the cold front. And you should imagine the warm conveyor belt, you have warm, sometimes moist air, crosses the front and enters a region that is really cold and sometimes really dry. And so you have precipitation that is falling into essentially into dry air. Dry air, low relative humidity leads to a lot of evaporation, and the evaporation can actually lead to pretty strong mesoscale downdrafts that help the propagation of convective systems that are often associated with anaphrons. So anaphrons sometimes are associated with things like squall lines when they propagate. An example of a squall line is you can see in the bottom figure. So you have convection that is developing on the edge of the front, and then as convective cells age and kind of die, they move to the left, and they keep precipitating. Precipitation generates relatively strong mesoscale downdrafts, and these downdrafts help the generation of new cumulonimbus clouds. I will not go too much into details with squall lines because we will talk about squall lines and convective systems later on. But if you have any questions, if you want to know more right now, please let me know. Okay. In general, anaphrons have been observed to be associated with. I said anaphrons. Yes, anaphrons are associated with heavier precipitation than cataphrons typically. These two are not mutually exclusive, and sometimes cataphrons and anaphrons can both appear at different stages of the life cycle of a cold front. Okay. Well, if we have a cold front, then we will likely have a warm front, and I won't say much about warm fronts for the main reason that relatively little is known on warm fronts. Warm fronts are still kind of not really well understood, and there are many aspects that are not particularly clear. One thing that is known is that the propagation mechanisms of warm fronts are different from those of cold fronts. Cold fronts are characterized by cold and dense air that propagates often very close to the surface and kind of moves on. Warm fronts, because they're characterized by the advance of warm air, it's unlikely that the warm air will advance at the surface, because that would be convectively unstable. And so often warm fronts propagate from higher up. And so the mechanisms are a little bit different. Warm fronts rely more on turbulent mixing in the atmosphere than cold fronts do. Okay. We have an example here of the propagation of a warm front, and this is from 2010. Propagation of a warm front in 24 January 2010, and the bottom figure shows essentially sea level pressure and the warm front over the Carolinas, sort of on top of the above Florida over the Carolinas. The top left is a sounding that is taken in Peachtree City, Georgia. And the one on the top right, the figure on the top right, is a combination of isotopes in dashed lines, and the black lines are 850 millibar geopotential heights. Yes. Okay. And so we have the advance of warm air, essentially from the south, that is sort of making its way along the East Coast. Notice how, if you look at the sounding in Georgia, notice the really strong change. Talk about the front not being at the surface. Look at the temperature. I don't want to say discontinuity, but the really strong temperature difference between 925 millibar, where temperature is 5 Celsius degrees, and 875, 900 millibar, where temperature is almost 15 degrees. So there is a 10-degree shift, essentially in a matter of a few hundred meters, a few tens of meters even. And interestingly, this layer is almost completely saturated. Up to 850 millibar, it's almost completely saturated. Probably not foggy, but very close to being foggy. However, notice also that temperature until 700 millibar is above freezing, meaning that the region where you have clouds here is above saturation. So again, unlikely that you have mixed phase clouds. So this is likely either lightly precipitating or non-precipitating at all. Okay. Next in line is the occluded front. Okay. Now, there is a little bit of debate as to even what occluded fronts are and how we should think of them. Occluded fronts are typically considered as a stage in the development of an extratropical cyclone. This something to the extent of an occluded front had been hypothesized by the Norwegian model already, and the idea was that pretty much when the cyclone develops, when it reaches full maturity, an occluded front is developed, and the cyclone then slowly, more or less slowly decays. Okay. I'm a little reluctant to say this because there's a few caveats that have to go with it, and there really isn't a consensus in the community, if you will, as to as to this, but essentially the idea is that fronts get occluded when the cold front, that moves faster than the warm front, overtakes the warm front. Okay, so this is an example, sort of a sketch of this is a numerical model simulation. Okay, you can see the cold front over from southern Illinois, where there's a low, all the way down to, I want to say, Louisiana or Alabama. I'm sure Joy would correct me if we were in class. At hour 21, this is the situation, and then you have the warm front to the north. Hour 27, the cold front is moving. Warm front is not really moving all that fast. And notice that the two start to coincide right underneath the Great Lakes. And hour 30, the cold front has overtaken the warm front. There is still some controversy because some people say that not all occluded fronts arise like this, but it seems that many arise this way. It's a good way to conceptualize, if you will, but just keep in mind that that things are a bit more complicated than this. And finally, last thing I wanted to mention were coastal fronts. Coastal fronts are relatively common in the U.S. because the U.S. has has many coasts. The West Coast, the East Coast, and the Gulf of Mexico. Coasts can be, as you can imagine, I would say perhaps even particularly during the winter, they can be regions of enhanced temperature gradients. During the winter, for example, the ocean remains warm, but the land doesn't, and the land can cool significantly at night. There are usually breezes that originate. We'll talk about those later on. And these breezes essentially, push warmer, colder air. For example, they can push warm or cold air. They can push warm air towards colder air. And according to how the synoptic conditions are, and according to how the temperatures are distributed over land and over the ocean, there can be a front that is generated. So in the figure here, we're seeing northeasterly flow that is pushing air towards the land. Land cooler than the ocean, okay? And so the ocean has warm marine air. The land is colder, but at the same time, we can have some kind of a breeze that is originated for whatever reason, and this brings essentially the two air masses to quote-unquote collide, okay, or to be really close together. This generates temperature gradients, and as you can imagine, this is another way of seeing a front. And these are important because these can persist for a long time, and these can lead sometimes to heavy precipitation. Some of the characteristics that are important to keep in mind that are often observed with coastal fronts is that there is usually shallow front that separates the cold continental air from warm maritime air. These have the structure more or less of warm fronts, if you will. So not so much like the cold, with the sort of avalanche that's propagating, but something more like a warm front. They can have precipitation, and the heaviest precipitation often observed on the cold side of the fronts. And sea level pressure often exhibits an inverted trough-like pattern. And also these can be the sites for cyclogenesis. These sometimes are associated with cyclonic vorticity. And so the existence of something of a coastal front could enhance the vorticity, for example, of a trough that is passing by. If a trough passes by a coastal front, it could pick up really soon, and it could generate an extratropical cyclone. Okay, I think this ends all I wanted to say about France. Next class will be a lab, and so I will not record any lecture, but you have the instruction. You have chapter 6 of the manual, so this is what you will do for the next class. I will send a reminder through Laulima. I would like to ask you now since we will not have the weather map discussions, and I would encourage everyone to not come together to work in teams, but do this individually. Instead of having the usual map discussion as we did in class, I would encourage you to pick a region on the mainland or anywhere in the world and write a paragraph or two on the past weather in this region, current weather, and future weather conditions. So same map discussion that you'd have done in a team on the board, but now you'll do it on your own, and you should send me an email. You should submit a written paragraph of this. The weather challenges are still continuing, and with this said, I imagine there will be plenty of questions. Let me know your questions through email, text, direct messages, anything that you could think of. If there was something else that didn't work, please let me know. If there's something else that you'd like to see done differently, please let me know. And otherwise, I will see you for next class, in which we will talk about a beautiful subject, which is baroclinic instability. Thank you very much, and please take good care of yourself.